Okay, good afternoon and welcome to tonight's session. I'm Helen Haralambous from MAB and I'll be your moderator for tonight's session. So while I'm admitting people, please keep introducing yourself, and that'd be nice so we can see who we've got. So tonight's session will be presented by David Rogers. But before I introduce David, I'll just start with a quick acknowledgement to country. So I acknowledge the Wurundjeri people, the traditional owners of the land upon which Mav and I are currently located. I also acknowledge the traditional owners of the land upon which you may be located as you attend this conference. Our respects to elders past, present and emerging. We acknowledge the First Nations people who continue to contribute to the work of improving Indigenous education and learning and research, and to those First Nations students who are learning with us across Victoria. Okay, just a couple of little housekeeping protocols, etc. You were all muted upon entry, but we obviously don't want that to stay that way. So we ask you to keep your mic muted while David is speaking. However, there are times where we would like your participation. So we do appreciate at that time, if you're asked a particular question or if David wants a response, then please unmute and ask your question. We will have some question and answer time towards the end as well. So feel free to ask then. If in between you would like to ask something and it's during the session, then feel free to also type it in the chat, and I'll keep an eye on that and let David know if I think it needs to be addressed at that particular time, because it's relevant to what David is chatting about at the time. We'll do it then. Otherwise, we'll keep an eye and go back to all the questions towards the end. So the session is being recorded. The recording will be uploaded to the MAV private YouTube channel, and then all of you will be emailed the link to the recording. Okay, so tonight I'd like to welcome David. So David is currently Head of Mathematics at Camberwell Grammar. David has had 20 years experience teaching maths methods and Spech. He's an assessor for Specialist Maths Exam 1 and has been Chief Assessor for Special Maths Exam 1 since 2018. David is also writer and presenter for MAV for both the Assessors series and with our trial exams as well. And I know he is quite keen on this particular topic and has presented a similar session for methods, which was very well received. So I will mute myself and stop sharing, and we'll allow David to make a start while I continue to admit people. And while you're waiting, please continue to introduce yourself in chat. So we're just having a quick look at where we've got people from. So
yep, great, thanks Helen. Let me just sort out my screens and such things. Give me just a moment. I'll start sharing. Right. Share. Oops. Share screen.
Yes, we've got a few people from different parts of Victoria, from Shepparton to Warrnambool to Yarrawonga.
How's that looking, Helen?
Yes, we can see that. Thank you.
Excellent. No worries.
Okay, I'll mute myself then.
Excellent. Well, welcome to you all. A few familiar names and faces in the list, which is great. Yeah, so we'll be talking about pseudocode in VCE specialist maths tonight. Now, I don't claim sort of any sort of particular expertise here. I guess I've sort of been thinking about it, and I've been talking to special teachers at conferences and sort of just sort of around the traps. And there was, and I know, Helen and the MAV sort of picked up on this as well. There was definitely, a certain amount of trepidation or nervousness about this new topic in the specialist maths course. And I guess in talking to people, I sort of thought, well, maybe if I can perhaps, I'm coming in from sort of the, much the same as everybody else, but I think I think in what I've sort of thought about it and read about it and been working on, I think there's really nothing too much to get too worried about. So hopefully that's part of the aim of this afternoon or this evening's presentation. So I'll just sort of tell you who I am. So some of you know me already because you've worked with me over the years. But my background is in mathematics. So I started out in pure mathematics, in algebra in particular. So I came from a background in algebra. And then sort of came into high school teaching, and I've been at Camberwell for this is my 21st year actually, and the last 15 or so, well, most of that now. How about that? As head of maths, and I've been teaching spec here at Camberwell ever since I set foot in the door. And maths methods most of those years, and university enhancement maths, the uni maths, the Melbourne Uni maths program, which if you don't know about, sort of I'll just put in the plug for it now. If you don't know about it, look into it. It's a very, very good and interesting program for your top students. So especially for we're specialist maths teachers here, so we get to see these students if you're looking to have them challenged, and there's a nearby uni maths venue. See about for next year's students, see about sending them on. As Helen said, I've been involved in exam 1 assessing for quite a few years, and I can see in the list here some of the people with whom I assess, and we've just actually the end of last week and the start of this week finished wrapping up the Northern Hemisphere specialist maths marking, which of course is interesting because this was the last time last time for a little while at least, that we've had the mechanics material on the spec exams. And so for end of year this year, the new course with proof and pseudocode and all the rest of it, all the really nice vectors stuff will be there. But there'll be those other things as well. Okay, so I guess the aim of the session is to look at some basics of pseudocode, and for those, I know there are a couple of you here who were at the maths methods session, a few weeks ago. The basics stuff will be much the same. No real difference there. But I will sort of look at some different examples later on, sort of perhaps examples more relevant to specialists. But the basics will be much the same sort of presentation as I gave to the methods people. And really, the third point there is kind of what it's all about. I just want to demystify perhaps and remove, hopefully, some of that nervousness about pseudocode in the spec course. I don't think there's too much to be nervous about. Especially not this year. We'll see what happens in coming years, but I think at the moment we should be we and our students shouldn't be too nervous. Okay, so just to start off, what is pseudocode? So if you don't know, if this is completely sort of completely new to you, it's probably not. But if it is, if you've never sort of heard of this or thought about this before, all it is, it's a way of writing down a sequence of steps, a sequence of steps for some sort of algorithm. And an algorithm is really, the recipe for making a cake is an algorithm. Get some flour, get some sugar, get some eggs, mix it up, do this, put it in the oven for a certain amount of time, take it out of the oven, let it sit. That's an algorithm. It's just a sequence of steps. Pseudocode just allows us to write down this sequence of steps in sort of an easily understandable plain language, which may well later on be translated into computer code, into some computer language. But at the moment we're trying to get sort of the idea of what's happening with our algorithm. It may be that there's some sort of natural structure, some sort of looping or repetition going on, and we can capture that in pseudocode. That's the idea. You don't have to know how to program in any particular language. That's not really the aim of the game at the moment. In VCE maths, that may change in the future, but that's speculation. Okay, so if you're looking at the current study design, which is new for this year, you'll see that pseudocode appears through maths methods and specialist maths. It's not specifically part of the foundation maths or the general maths courses. There are elements of sort of algorithmic thinking, no doubt, through those other courses, but pseudocode is specifically mentioned through the maths methods and the specialist maths courses. And if you're looking at the specialist maths parts of the study design, you'll see it. You'll see it in outcome 1, which is your basics, defining and explaining key concepts. And you'll see interpret and apply algorithms in a variety of contexts, including the use of pseudocode. So this is in outcome 1. And outcome 2, applying mathematical processes in non-routine contexts. So here we've got key knowledge and key skills, which both refer to pseudocode and algorithms. Representing some of the tools that we might use in specialist maths. Obviously you're thinking things like Euler's method and so on. Representing these in sort of an algorithm form and writing down the steps as an algorithm. And finally, in outcome 3, which is the use of technology broadly, to investigate and model, and we can see again computational thinking, and algorithms coming up here through here. So it's through this study design for specialist maths, just the same way as it is for maths methods. It's obviously something that has become a big part of our courses. I mentioned this a few weeks ago with the math methods people, and just talking about algorithms and algorithmic thinking in the Victorian curriculum, and I'll mention this a bit later on in the talk again. But if you look at, say, year 8 or year 10 maths, there's this notion of algorithmic thinking through that sort of middle years of mathematics as well. And I wonder actually how many of us can hand on heart say we're actually doing this with our year 8, 9, 10 students, and I suspect probably a lot of us aren't. I actually perhaps wasn't even aware that there were some of these things in the Victorian curriculum until I started sort of looking through this. So certainly, I don't think there'd be many people using pointers in algorithms, in their year 10 courses. But these things are listed there. So it's obviously something that is deemed as important. Okay, now as we sort of move into looking at some actual examples, there's no standard way to write pseudocode. So for those of you who are teaching Spesh this year, no doubt you've looked at the sample exams and you've seen the pseudocode, in the specialist maths exam 2, and quite possibly you're also teaching methods or involved in methods teaching, or have just out of curiosity looked at the methods sample papers, and you'll see the pseudocode in the methods sample exam, and you'll see the quite different styles, the different ways of writing them down. If you look at the various textbooks, you'll see different styles. Again, if you look at the VCE website, which is the one listed there, you can just sort of Google pseudocode VCE and it'll take you to a website, and you'll see different styles yet again. So there's no standard, there's no universally decided standard of how pseudocode needs to look or needs to be written. It's lots of people do it differently. And I've said, there's no right or wrong, I guess, as long as it works, maybe. So I guess that moral of the story, a pseudocode is intended to be a way to represent an algorithmic process in some sort of human readable form. And before perhaps it's turned into an actual language. Python is quite popular at the moment, but obviously things like C and Java and Pascal and Fortran. I guess I'm showing my age. Okay, so let's start getting into it. So for those of you who sort of aren't, who are sort of rookies at this and just sort of getting started, thinking, well, we've got an idea here. We're going to write down some pseudocode that lists or prints or outputs in some particular form. The first 10 even numbers greater than 0. We use the word print. We're probably not printing this on paper. It's sort of it's sort of, I guess, anachronism, I guess, an old-fashioned kind of term, when we probably used to sort of print this out, because that's how we saw our output, but now it's just on a screen. So printing first 10 even numbers greater than 0, we just use a for loop. So you can see there we've got a counter there, which is the I. So each time we go through here with the counting, the value of I is incremented by 1. So I starts out at 1, goes through, so it prints out 2 by I, so it prints out 2. We then increment or increase the value of I by 1. So I now becomes 2, and we loop around again. And we do that as I changes from 1 through to 10. So it's just going to print out those numbers. Now, the syntax that we're using will have something like, whenever we have a for, the word for, we need to end it. We'll have an end for. The same when we do a while loop, we'll have while and end while, to sort of close the loop off. So that's pretty standard. There's nothing too clever about that. The while loop is much the same thing. It looks a little bit different, but here, instead of counting sort of explicitly 1 through to 10, what we've got is this idea of some sort of testing or checking to see if some condition remains true. So here we'll we initialize the value of I, so we'll say I is equal to 1, and as you can see in that little box there, that left pointing arrow is a fairly standard way to sort of initialize that symbol, that variable to a particular value. So we've said I is 1, and then we've got this while loop. So we've got the while, and a couple of lines down we've got the end while, and that sort of closes the closes that little looping process off. And so we're going to go into the loop. So print 2 by I. So first of all print 2, and then the value of I is incremented by 1. So we've explicitly, you can see there, we've sort of explicitly incremented the value of I. So we've increased it by 1. So I now becomes 2. We go back to the start of the loop. The check is done. Is 2 less than 10? Yes, it is. And so go into the loop and now print out 4 and go through all the way through. Ultimately, once I is 10, go through the loop, print out 20. The value of I is increased by 1, so it's now 11. We go back to the start of the loop, the while part. I is now 11, so the test is done. Is 11 less than or equal to 10? Obviously it's not. And so we jump out of the while loop, and that's the end of it. And that's a fairly simple sort of procedure, fairly simple sort of process that's happening there. Now you can do more interesting things. I like being sort of being the person I am. I like to talk about mathsy type things. Just printing out lists of even numbers or odd numbers is hardly very interesting. So naturally, we want to start talking about prime numbers and things like that. So here I'll have some pseudocode that prints out prime numbers smaller than 30. And so we've got, there's a couple of little ways to do this here. On the left, there's a for loop. So from I equals 1 to 30, so this will print out the primes smaller than 30. If I is prime, we'll print out the prime, the prime. So it'll start with 1. It'll say is 1 prime. No, it's not. Then it'll move on to 2. If 2 is prime, we'll print it out. You can see that there's, we've got that for loop. So I'm just looking at this example here on the left here. We've got the for loop sort of closed by the end for, and in between there we've got this this if. So it's a little test, a little checking thing, which says, if the value is prime, we'll print it. If it's not, we don't do anything. We just ignore it and just cycle around like that. You can do it with a while loop as well. It's much the same thing. So we've got that simple if statement in there. Fairly simple, nothing too fancy. Here's another sort of a variation on this. So you might want to ask, well, let's have some pseudocode that prints out the first 10 prime numbers. So this time, I don't know how far I need to go to get 10 prime numbers. I don't know how many integers I need to go through until I get to the 10th prime. So it's a bit harder to sort of have a for loop here. The for loop won't really help me because I don't necessarily know where to stop. So what I'll do is use a while loop. And so here I've got a couple of counters here, a couple of variables there, an I and an N. They're both initialized to 1 at the start. And so N is counting the number of primes I've got here, and I is just an incrementing of integers. This will go as far as it needs to go. It'll just sort of keep on going around until I've got enough primes. So in this particular bit of pseudocode, you can see, yeah, we enter it. Yeah, so starts off with I is 1 and N is 1. So N is, yeah, N is definitely less than 11. So yeah, we're good. Go into it. If I is prime, we're going to print it. And then the N value is incremented by 1. So at the moment I is 1, it's not prime, so we're not going to print it, and we're not going to increment the N value by 1, but we'll increment the I value by 1. So we'll move into that lower section. We'll increment the I value, and then go back round again, back to the start, to that N value. Now I is 2. It is prime, so we'll print it. So we'll print out 2, and we'll increment the N value because we've got 1 prime down. So now we're looking for the second prime, and we'll just keep on looping through like that until yeah, this will end when when I've got my 10 primes. When I've got my 10 primes, hopefully. So this is the example from the specialist maths exam 2. It was multiple choice question 2, I think, on the exam. And so we've got this bit of pseudocode there on the left. So the notation that the writers have opted to use here, yeah, they're actually, it actually looks a bit like how a computer program might actually read. Obviously, in my sort of earlier examples here, I haven't said specifically that I and N are integers. The exam writers here have said, well, yeah, N is an integer, F is an integer, T1 and T2 are integers. So they're sort of declaring from the outset what sort of numbers these are. If you didn't need integers, if you needed, say, real numbers, you might declare real. Obviously, if you were in a programming language, it might be more typical to use the word float or something like that. So we can. This was the example on the sample. It's not too hard. It's not too hard to do. It's fairly sort of simple little exercise. But what I've sort of tried to sort of highlight here is the idea of using a trace table or a desk check. Now this is this little table down the bottom here. Let's grab my so this is this little table down the bottom here. So down here, where you can keep track of the various symbols, as you go through the process. What's happening to the F value, what's happening to the T1 and the T2 values as you cycle through or loop through this this particular algorithm. So we can see at the start we've got our F value is set to 0, T1 and T2 are 2 and 3 respectively, and we're going to repeat this process 3 times. So you can see that's what's happened in the table there. The F value becomes the T value plus the T1 value plus 2 times the T2 value. Then T2 becomes F, and then we're going to print the F value. So you can see as this goes along, we're going to print 8, 18, and 38. We don't print the 0. If you notice, where the printing part happens, it happens after we've done that little bit of we've done this stuff with the F. So it's happened. We've changed the F value, then we print it. So the first F value that gets printed is actually 8, and then 18 and 38. So the final number in the list is 38. So if this was on a real exam, a number of students may well sort of choose the 18 option, option B, because they might be thinking, well, 0 gets printed, then 8 gets printed, then 18 gets printed. Yeah, that'd be wrong, because it's 8, 18, 38. It's simple. It's very, very simple. There's nothing too fancy going on here. But this idea of that desk check or trace table is a really handy thing that you can get your students using for sort of running through the steps and seeing basically keeping track of what's happening with the symbols as you go through. Now, often we want to define functions. There are various ways of doing this, and I just want to sort of indicate the couple of methods that we've seen in the VCAA sample papers. So here we want to, in this sort of particular example, we want to write down some pseudocode which outputs the result of evaluating the function f of x is 2x plus 3. Basically, like a year 8 or year 9 table of values. we want to produce a table of values, or at least the y values. And so we need to define the function. So a typical way to do this is simply to sort of do something like that. Define f of x, and then when we have this this word return 2x plus 3, that's saying that f of x is set to be 2x plus 3. It's basically it may well be the kind of thing that in an actual computer program you're asking for some response from the command line or the terminal or whatever. It asks for you to enter what the function is, and then goes away and does something with it. So you could put in a different function and get a different set of outputs. I've got it there with a with a for loop, which is going to print out the 10 values. And then on the right hand side, we've got the pseudocode which outputs the result of evaluating this same function while the value of f of x is less than or equal to 30. So this again is that while loop. It's doing a little test as we go through. It's testing to see is the f value, the y value, if you like, less than 31, and as long as it's less than 31, we'll keep on going through, and we'll keep on churning out numbers until this whole process needs to stop. So there we go. You're pretty straightforward. A couple of things going on there. I mentioned this last week with a few weeks ago with the maths methods people, just because it's an interesting problem which sort of lends itself quite nicely to algorithmic thinking and writing out pseudocode. If you're not familiar with the Collatz conjecture, I know a lot of you will be. But if you're not, have a look at this. Have a look at this. There's some absolutely marvelous videos on YouTube. For instance, the number file people have got a couple of videos on the Collatz conjecture. And it's really easy to understand problem. I call it a problem. You can get your younger students. You may not want to spend any time with your year 11 and year 12 students necessarily doing too much of this, but it could be interesting if say year 11s. But certainly younger students can understand this. What you do is you start with a number, pick any number, any natural number, and start with a positive integer and run through this process. If n is even, if your number is even, halve it. If it's odd, you triple it and add 1, and that of course gives you a new integer. And then you apply that rule. So you can see there's that repetitive process. There's that looping around naturally in here, which lends itself to writing down an algorithm or pseudocode. And the Collatz conjecture actually says that, well, this sequence of numbers will always end in 1. It's a conjecture. This is not. There is no proof of this. And the very, very famous itinerant mathematician Paul Erdos said of the Collatz conjecture that mathematics may not be ready for such problems. Similar things have been said about the Goldbach conjecture as well. That our language of mathematics just can't deal with these things. It's such a simple problem, but the mathematics behind it sort of escapes us, the actual proof. So you can see I've got an example there, starting with 17. It's odd, so triple it and add 1, you get 52. Halve it, you get 26. Halve it again, 13. It's now odd, triple it and add 1, takes you to 40. Halve it, 20. Halve it again, 10. Halve it again, 5. It's now odd, so triple it and add 1. And then, an interesting thing that your students should recognise is that when we tripled and added 1 to 5, we got to 16. 16, of course, is a power of 2. It's 2 to the 4. As you halve it, you go to 8, 4, 2, and down to 1. Now, of course, once you get to 1, it's odd, so you triple it and add 1, takes you to 4, halve it, 2, halve it again back to 1, and so you're in this sort of this infinite loop of 1, 4, 2, 1, 4, 2, 1, 4, 2, 1, and so in your algorithm that that students might write down, they would have some sort of some escape there to say, well, if it gets to 1, which the conjecture says it always will, if it gets to 1, just stop. You don't need to continue the process. So there's a bit of you can write sort of a function there. I won't go through all this, but it's there for you to look at. There's a bit of pseudocode written there. I've used the modulus function here. You can see it up here. There we go. There's the modulus function. Is this not modulus as in absolute value? It's mod as in what's the remainder after the number is divided, in this case by 2. That's if the remainder after dividing a number by 2 is 0, then that number is even. If the remainder is 1, then the number is odd. So that mod function is a natural tester for even and oddness, which of course you need here. So you can use this in a Collatz algorithm. Okay, so I'll move on. The on that VCAA website, which talks about pseudocode, it mentions a few areas where you could use where pseudocode might crop up. So obviously, in sequences, partial sums, so this means adding up the terms of a sequence, to get a finite series, sums and products, of course. Perhaps more relevant for year 12, numerical integration. So Riemann sums, Riemann sums, in this context just means sort of adding up areas of rectangles, volumes, surface areas of solids of revolution, arc length of a curve. These are just integrals. They're just, no matter how sort of complicated the integrand might be, the integrand, for the surface area generated with a volume of revolution, it's a 2 pi y square root of 1 plus dy dx squared. So something like that, whatever it is. But it's just an integral. It might be a complicated integrand. But ultimately, it's just some function integrated between terminals. So it lends itself to numerical evaluation, and again, you could use Riemann sums, or obviously our specialist maths students are doing maths methods. The trapezium rule is part of maths methods, so you could imagine combining this in a SAC with the trapezium rule. Vector operations, the scalar product, cross product, projections. I'll talk about this in I've got an example here in a moment of the scalar product. The scalar product has a natural loop in it. You need to multiply some products. So you need to add some products together to find the result of the scalar product of two vectors. Cross product is similar. Euler's method, we're very familiar with this. Obviously, this has been part of the Spec course for a long time. So Euler's method, we're all familiar with it, and it's it's obviously a highly algorithmic method. Even though it's written, we'll talk about this again in a moment. You can apply this to probability. You can do sort of problems in stats and probability also lend themselves to this as well. Using random numbers, instantly, my mind, this again, I haven't put this in the slides, but it might be something that some of you want to sort of look up later on. Monte Carlo methods. If you want to have something to talk to students about at some stage, you might want to show them how, say, the value of pi, for instance, can be approximated using a Monte Carlo method. Monte Carlo, like the biscuit, but actually perhaps referring more to the casino and the element of chance. So with the scalar product, let's quickly sort of go through. So I won't go through all my examples because you can look at those at another stage. But the scalar product of two vectors, we're all very familiar with with the scalar product. Hopefully there aren't any typos or anything in here, but anyway. It's often convenient. We're not going to enter into our pseudocode i's and j's and k's. Essentially the I and the J and the K for a three-dimensional vector are just placeholders. Obviously the uni maths teacher in me is of course thinking, well, it's not just placeholder, it's they're the basis vectors for the standard basis, but that's we can think of them just essentially as placeholders giving us coordinates as a triple. So the vector A, we might just write as a triple, A1, A2, A3. The vector B is a triple, B1, B2, B3. It's just an array, if you like, of numbers. And there are different ways of representing arrays in pseudocode. I've decided to call an array a list of symbols here, with square brackets around it. The square brackets are indicating, it's an array, and I'm just separating the entries by commas. I can, select, an entry from an array, simply by doing as I've done down here. If I want the first entry from the array called A, I'll just do A in the square brackets 1, and that'll spit out the value A1. A2 will be the symbol A2, for instance. It's just a way of representing this these lists. So here's a fairly simple one here. All I'm doing with the pseudocode on the right hand side, I've got some process which is going to compute for me the scalar product of the vectors 3i 4j minus k, 5i 2j plus 4k, and it's just a simple loop, isn't it? That's all that's really going on there. I start out, I've initialized some variable. I'm going to call it prod, prod for product. I'm calling it, setting it to 0 at the start. And then what I'm going to do is just cycle through this this for loop, and at each time, starting off with the first one, so A1 and B1, so it's going to compute 15, and it's going to add that to prod, which currently is 0, so 15. Then it'll add 8, then it'll subtract 4, and that'll finish it off, and the output will be hopefully 19. So that's kind of the idea here. A very simple thing. A cross product. So there's no doubt various ways to do this. I've sort of elected to do this sort of perhaps a naive way, sort of the way we would. I'm sort of trying to replicate how we might do this by hand, by using determinants. Obviously there are ways you could just sort of pretty much just hard code this in. But I'm sort of trying to replicate what's going on by hand, and so I've got an idea of a determinant here, an AD minus BC. But perhaps what's worthy of note here is what I've got at this little stage there. I've got this -1 to the power of I plus 1. You might be wondering, what on earth is that doing there? Well, that's there, of course, to produce the sign changes. If you remember, the determinant here, it starts off, when we're computing A cross B, starts off with a plus, and then a minus, and then another plus. And so, hopefully as we go through, we can get that that flip-flopping of signs from plus to minus. That's really all that's happening there. It might not be the cleverest way to do this, but at least it's it gives a taste of what's going on. Naturally, sort of Euler's method. This is actually an example of some pseudocode for Euler's method on the VCE website. So they've done it with a while loop, which is fine. I've done one here with a for loop, at least just to sort of make it a tiny bit different. So Euler's method, formula's on the formula sheet, and we've been using it for years and years and years. We're all very familiar with Euler's method. And typical exam questions are find an approximation to to a certain value of the function, which is the solution to the DE. With a certain number of steps. Just sort of by the by, I'm a big fan of writing out my steps of Euler's method like this. Whenever I see students just writing down sort of just a bunch of steps down the page, changing values. It all just looks rather random. I come from a background of before pure mathematics, it was applied mathematics and mathematical physics. And no numerical analyst in their right mind would do anything other than write out tables like this. So tables like this are very routine, and it's definitely the way to go when you're doing things like Euler's method. But here on the right, we've got some pseudocode here, representing what's going on here. So we've defined a function. It's a function of x and y. I see no reason, why we should sort of restrict ourselves to differential equations in just a single, in a single variable. Here we've got essentially it's a separable differential equation, if you like. This particular one, it's probably easy enough to solve, and it actually is easy enough to solve by hand. You could do this. Exactly and get an analytic solution. But we've just got this idea of a some sort of looping process. Here, what I've done is I've specified this in this Euler program. We've got the starting values, the x0 and the y0. We've got the h, which is the step size, and n is the number of iterations we're going to do. Now, obviously, if you want to start at a certain point and end at a certain point, and use a certain number of iterations, well, then your h value is set for you. So you could write this differently. If you said you could use h is what is it, b minus a over n if you wanted to, if you set this up in a slightly alternative way. But again, this just loops through n times. You're going to do n cycles of this, and essentially what we've got here in this line with this the changing y value is just what's on the formula sheet. The new y value is the previous y value plus h times the previous derivative value, and that's all it is. So look, if I was a gambling man, I'd be thinking, come exam time, I wouldn't be too surprised to see examples like this, doing things like Euler's method. Maybe not this year, but in years to come, certainly you'd expect to see this. Almost certainly it's natural for specialist maths to have this kind of stuff in there. I was just sort of thinking about, because I talked about SAC ideas and such things for the maths methods people a few weeks ago, and I was thinking of a few things that could happen there. But for our special students, be nice to sort of think about, second order DEs, our y double dashed differential equations. And I certainly remember back at university doing these kinds of things and setting up a system of coupled first order differential equations, and you can then apply Euler's method to much more complicated second order differential equations. It's not part of the course. I just sort of looking around the other day. It sort of occurred to me that maybe this is actually part of the higher level IB. I know zero about the IB. I've never had anything to do with it. But just the references that came up seem to indicate that it might be part of the IB. Wouldn't surprise me, because it's the kind of thing that if you were feeling particularly motivated, you could certainly come up with some sort of investigation or application task or something which could touch on this. It's not that hard to do, scaffolded and motivated appropriately. I'll leave that there for you. I'm not going to sort of go through the intricacies of it this evening. But obviously that last point there, how might this be written in pseudocode? Well, there's that connection. I always think, whenever we're doing, numerical integration, for instance, in maths methods, we've got, in previous study designs that we just talked about rectangles. Well, now in the current methods study design, we've got access to the trapezium rule. But those of you who've been around, a while will remember, back in the, been a while since we've had it, but in the specialist maths course, things like Simpson's rule, for numerical integration, quadrature. So Simpson's rule. Well, you could also apply those same sort of ideas. How could you extend Euler's method? Well, there are, Euler's method is really your first order approximation solution for a differential equation. Every engineer has certainly encountered your RK4, the classic Runge-Kutta method for numerically getting a numerical solution to a differential equation. And you don't necessarily need to go through any of the great details of it, but sort of getting students to sort of investigate this a little bit, and writing out some pseudocode, and perhaps even if you're feeling particularly ambitious, you could even get them to write some code. I'd kind of love to see that happen. Whether they're doing it on the CAS calculator or whether they're doing it actually at a computer. I think there's scope to do lots of really interesting things. There's our numerical integration. This is from my maths methods slides. I'm just going to sort of mention this now. And for those not aware, who sort of haven't looked so closely at maths methods, perhaps the pseudocode for the trapezium method, or trapezium rule, was included in the sample exam. So students had to sort of run through some iterations of a trapezium rule calculator. So given that methods is a co-requisite for specialists, it would seem reasonable to to have students look at, say, volume of revolution, write down the integral, but then use the trapezium rule, perhaps write out an algorithm or some pseudocode to find the approximate volume, an arc length problem or a surface area problem. Doesn't matter too much which. So there's all of these kinds of ideas. These are just ideas which sort of occurred to me that you might want to sort of you might want to sort of see how you could sort of follow through and sort of develop into interesting tasks. It'd be pretty natural to sort of want to start looking at the surface area of a solid revolution, which of course is new to the course this year. So naturally you'd want to be sort of looking at those sorts of things. Okay, I'm going to sort of continue, sort of wrap it up in just a minute, but I just wanted to sort of draw your attention, to perhaps other sources of pseudocode examples. And some of you may be familiar with this, and some of you may not be remotely familiar with this. But there's an entire sub VCE subject, software, the computing software development subject. And if you look through their past exams, which just like our maths exams are on the VCIA website, you can find numerous examples of simple pseudocode, examples, often sort of multiple choice questions. When you're trying to sort of help your students run through these sort of iterative processes, doing trace tables or desk checks or whatever, and you want a ready source of problems, well, there you go. You can go to town with these things. There's lots of problems you can perhaps access. There's another one there. Yet another one. I'll also, just in sort of the final moments, I'll draw your attention to this. It's sort of I guess something that we do here at Camberwell. In some ways to sort of tick those boxes, through the for the Victorian curriculum, Australian curriculum, whatever. We talk about students having some exposure to algorithmic thinking. Well, there's an entire competition run by the Australian Maths Trust, which is the CAT competition, the computational and algorithmic thinking competition. And there's it's like the maths competition, which is maths competitions in August. This one's a bit earlier on in the year. Just asks students a range of questions, starting from sort of fairly easy through to sort of quite sophisticated problems. They're a bit different to the maths questions, because they are often written in this sort of pseudocode way. You need to be thinking about sort of data structures and looping and iterative procedures to get to some solution. There's another source of interesting problems that perhaps might be useful to you and or your students. Even at the younger years, there's this competition runs from primary school level through to year 12. So good source of problems there. And I'll just sort of mention this is just entirely my sort of me just sort of speculating and sort of thinking out loud more than anything. We can see there's definite trend. It's coming through through the younger years, of course, with the Australian curriculum, Victorian curriculum, but now it's firmly in the maths methods and specialist maths study designs. There's no requirement at the moment to actually be writing any code. That was one of the fears that I know when I was talking to people last year and early this year when the study design came out. There was a number of specialist maths teachers, our colleagues, expressed to me and to other people, no doubt, this concern that they would have to be writing computer code, actually programming code, compiling and running programs, and that's not the case. It's so certainly not at the moment. It's not the case. Might this change in future study designs? Well, it might. It may well. There are people better placed to sort of answer that and speculate about that. But it may well change. But this probably seems like a good idea, because really all of our bright maths students will be going on to be working in data intensive fields, be it science, be it engineering, wherever. They'll be working with data and working with people who are programming, and they'll be expected to interact with these people. I sort of mentioned at the very start, I've just finished marking the Northern Hemisphere papers, and it was sort of the farewell to the mechanics material. So you're marking those last papers with the mechanics questions on them. So of course, mechanics has come out, and in its place. We've got more vectors. We've got the proof and logic, and we've got the the pseudocode is coming. Is the loss of mechanics worth the introduction of those new topics? I don't know. People will have opinions about that. We're still using CAS. I personally use Mathematica, myself, as sort of a daily driver. Really, the CAS calculators, the actual physical CAS calculators irritate me hugely. I love CAS. I love using computational tools, but just the restricted nature of a CAS calculator is well, it's just that, very restrictive. You can do amazing things in Mathematica, and of course, if you go a bit further on, you can actually access any number of programming languages. Your students quite possibly are familiar with things like Python. I know a lot of my students already are. They know how to use languages like Python. I've never really played around with them. Sort of I've tinkered with it, and it seems coming from somebody who used to write code in C and in Fortran a million years ago, Python is incredibly intuitive. It's very easy to read and work with, and our students pick this up really quickly. And I'd also like to put in a little plug there at the bottom. There's perhaps more for sort of the general maths people. There's some great software out there for statistics, and the one I mentioned is the one called R. If you don't know about R, do look it up. It's completely free and open source, and you can do some amazing statistics computations there. So that's I've just gone over the hour, but hopefully the idea was I'll sort of stop sharing that now. Just get rid of this for now. I'll go back to there. You can see Helen there. She's pinned, I think, but that's here we go. We can hopefully I've the idea was I'm not going to sort of give you the everything you possibly need to know in for pseudocode in the space of in the space of an hour. That's not going to happen. You'll need to look at the sample exams. You'll need to no doubt the commercial exam providers will have pseudocode examples on their practice exams. But also, the textbooks, the usual ones we go to, the Cambridge and the Maths Quest and the Nelson or whoever else write textbooks. They've all got lots of pseudocode examples and things you can do there with pseudocode. So hopefully, the purpose of this evening was just to hopefully sort of make it so that you sort of you can feel a little more comfortable about this. It's nothing to be too worried about. I'm sure for this year, it'll be a sort of fairly gentle, gentle introduction to pseudocode. In our specialist maths exams, it should be fairly straightforward. One would like to think, and hopefully you feel a little more comfortable, with it. So I'll say thank you for attending. Thank you for coming along. Thank you for listening to me. Hopefully it's been useful. I'll send my slides through to Helen, and no doubt she'll be able to make those available to you. You can do what you want with them. I'll put my email address in the chat right now. So if you feel inclined to contact me and ask anything, I don't promise I'll have the answers, but I'll give it a shot.
And while David's doing that, you'll notice I've put up a slide with a feedback survey. So please hover over that little QR code with your phones and complete that, especially the question at the end. Really, we based our PL program on your feedback. So this came about because I think there were so many people that said after the VCE conference that they wanted something on pseudocode. So please do that. I know David has gone overtime, as he said, and we really thank him for his generosity and his time. Thank you. And I'll also, while you're doing that, I'll also pop the link in, and I'll send it with, if anyone didn't get to do it, I'll send it with the recording when we get that as well. But I do know that sometimes it's a lot easier if people just do it as they're finishing off. Okay, so with that, I will once again, thanks David very much, and thank you all for your time as well.
No worries. Thank you, Helen, and best wishes to everyone for the end of term. 2.5 weeks to go.
Yep, good luck everyone. Hope you're not all too busy writing, correcting sacks and so forth at the moment.
Yep.